They call emergency 911. What's the address of the emergency? I need emergency! Mom, my husband is dying! My husband is dying! Come, 911! Now, please, my baby's not breathing! Okay, now, are you with him right now? He's not breathing at all! We all the way here! Oh, please, just somebody, he's dead!
Welcome back to the AEMT lecture series. Mike Morris here with you again. Glad to have you guys back. Chapter 7. And this will be the second video for Chapter 7. We're just going to kind of cruise through here. Hopefully you guys have had a chance to kind of review the material, because if you have, you should have some questions, and maybe you're confused because, you know, it's kind of a confusing chapter. But hope everybody's families, significant others are doing well during our pandemic crisis. Hope everybody's had time, you know, can get, you know, at least, what am I trying to say? Isolate, you know, when you're not here, you know, with the family or whatever. And just, I feel like we've went back in time. Kind of feel like that we're back when I was like the 70s when I was a kid, when there was no, you know, nowhere to go. Well, at least there wasn't for me. I grew up in a little poor town and farming town. So, yeah, so there wasn't a whole lot to do there. But that's what I kind of feel. It's like we've went kind of back in time, but this time will pass. It will pass, and we'll be back at it, going crazy, doing 1,000 things. Again, everything will be open. So I just hope everybody stays well. So chapter 7, here we go. Get your cup of coffee. This is going to be my second recording of this video because the first one was it was so long. I'm trying to condense that so I don't lose you guys. If you feel yourself drifting or something like that, just go ahead and pause it. Pause the video, stretch. Because the topics here are fairly deep, but don't worry, I got you. You need to know a little bit about what's in there, but you don't need to know the whole process, at least for, like, you know, some of the Krebs cycle. And they don't tell you in the Krebs cycle. I think if I remember right from school, there was like 8 steps inside the Krebs cycle. And so what they did in your book in like 4 or 5 paragraphs is try to describe the Krebs cycle. And it was pretty confusing when I looked over it. So but cellular metabolism is something that we should all strive to understand. And the reason why that is because they're going back to that first video when we talked about the organelles. There is a cost for severe respiratory distress knocking on failure's door, and that cost is hypoxia, and hypoxia eventually leads to cell death, right? So that's what we have to understand, and that's what, again, what learning about the cell is all about. Allowing you to put a cost factor in with what's going on with your patient. All right, so anyway, cellular metabolism is a process that produces energy. Living's not free. All right, living is not free. And so we're going to talk about that. We're going to talk about the role that oxygen plays in that process. And we're going to talk about the consequences of cellular hypoxia. All right. There's 2 types of the cellular metabolism that you need to be aware of, right? And one of these processes, right, is going to be, sorry, I'm getting a pen right here. All right, there's 2 types that you need to be familiar with: aerobic, which means with oxygen, and I'll say it again on the next slide, and anaerobic is without. And which of these two, right? Which of these two types occur will depend on the presence of oxygen inside that cell. All right, cellular metabolism and cellular respiration. All right, we'll talk more about that time, when we get to talking about the gas exchange process. But it kind of works like this. Glucose is going to cross. Glucose. All right, get my pen working here. Glucose right here, right? Let me get a different color real quick. All right, glucose is going to come into the cell, but what we're hoping that glucose finds is oxygen already in there. And through this chemical reaction between glucose and oxygen, we're going to get a chemical reaction that's going to produce energy. All right, so what we're hoping for is a chemical reaction that produces energy. All right, because living's not free. All right. So I mentioned a chemical reaction, right? So glucose is your primary fuel. All right. And then you have oxygen, right? Now, oxygen here is going to act as what we call a catalyst. Okay, and what a catalyst does is it increases the rate of the chemical reaction. So like a lot of businesses that make things like, I don't know, I can't remember, like top of my head, maybe we're going to say rubber, something like that. But they'll actually purchase these catalysts so that they can get their product out quicker than they would otherwise be able to do. So what I kind of like to think about is you have fire, right? You're at the house making a big bonfire. And yeah, you can sit there and set little twigs and, go small to big to get this fire going, and it'll go great. But who wants to wait for that? You're going to go in the garage, you're going to get some gas, right? Why? Because it's going to increase that rate of reaction. And so that's all oxygen does in this case. All right, so and continue. Bam. All right, so aerobic again. It's going to be the breakdown of molecules of glucose, all right, through a series of reactions that produces energy. And now we're going to produce energy in the form of ATP, right? And the goal here is to get, it depends on what book you read. The goal is to get 32, and I think our book might say 36. I have a slide on it later. Don't worry, I'm not going to hold you responsible for knowing how many moles of ATP. But, our goal is to get 32 moles. And that would be what we will get with aerobic, meaning with oxygen metabolism. And we'll talk about this some more in a second. All right, so glycolysis. So I'll say, it's in your book. And so let's talk about it. So again, glucose comes into the cell, and through that chemical reaction produces, I know it's hard to see, I can't see it, pyruvic acid. All right. That's what we're going to get. And we're going to get that We're going to get that pyruvic acid. Now, from here, we will go to glycolysis. And glycolysis can exist with or without oxygen. All right, so don't get confused. So aerobic metabolism, right, is with oxygen. Got to have oxygen to have aerobic metabolism, but you don't have to have aerobic metabolism to go into glycolysis. Glycolysis is a fail-safe system, because there's going to be times when there could be a time where you become hypoxic, and if that's the case, we need to draw on reserves. Problem is, the system is far from being a good fail-safe, because with aerobic, you're going to get 32 moles. Here, you're only going to get 2 moles of ATP. 2 moles is not enough to sustain us for very long, right? So that's what that's what you get. But glycolysis is where all this is going to happen, and we'll talk more about that in a second. Just kind of building you up to that point. So it's still anaerobic. So we talked about we get glucose coming into the cell, meets oxygen, which is the catalyst that'll ramp up the reaction. Right, it's going to increase the reaction. Then we're going to make some pyruvic acid right here. Okay, and that's good acid. It's not the bad acid that you'll see in a minute, which will in turn give us the energy, eventually give us the energy that we need, 36 moles. But look, I want you to see what other byproducts we get out of this. We get heat, we get CO2, carbon dioxide, and we get water. And this is almost as important as getting the energy, because heat, what are we going to need the heat for? Well, we need to preserve our body temperature, right? We need to have a body temp, right, of at least, 98.2? I mean, homeostasis. Remember what, homeostasis means? It means keeping the body in check, into a normalcy, right? And that's the cells require. That's one of their functions. Major functions is homeostasis, keeping things as normal or relatively normal as possible. All right. So, and they do that, one, by maintaining temperature, and so they, the cell does it by having that cell membrane that helps keep the temp inside here warm and not letting, the outside, in, so that it would cool it off. But regardless, we need that heat. We need that heat. So what else we have? We have CO2, carbon dioxide. Now that carbon dioxide, I want you to think about it for a second. Most of the time, 99% of the time, we're going to consider this waste. All right, so we're going to get rid of the CO2. And I don't know if you remember from EMT school, but, we're going to breathe CO2 off. We'll talk about that, as the chapter progresses. And then we get water. We get some water. And what are we going to use that water for? What do you think? I can just hear you guys, man. I bet you guys are making fun of me. We're going to use that water to blah, blah. I know that's what you guys are saying right now. But on a serious note, all right, we're going to use that water because for plasma. Because what is plasma mostly? Water. We're going to use that to transport blood products, right? Because, the plasma is the car and the products in whole blood, right? So what do you have? Red blood cells, white blood cells, and platelets, right? And they can't transport themselves, right? So you got to have the water to make the plasma. So do you see where I'm going with that? See all the advantages we get out of metabolism. And that's why it's important. So you can understand now when you're seeing somebody who's in failure, we're going to talk about what's going to happen to them, because they will definitely not be in aerobic metabolism, right? They'll be in anaerobic metabolism. And I like to remember the differences here. Aerobic with oxygen, but Anna is without, and Anna doesn't play. She's hateful. She's terrible. I don't care how much you try to get along with Anna. She hates you. She absolutely hates you. And she doesn't try to hide that either. She's straightforward. I hate you. Just straight up. Right? So that's why she's mean. And I can't really say what, because recording, and you'll use it against me in a court of law. But you know what I mean. So here we go. Glucose comes into the cell. Guess what, though? It doesn't meet that catalyst. It does not meet the catalyst. Right? It doesn't have the oxygen. Oxygen's missing. Okay. So there we go. Oxygen's missing. So what now? What now? What are we going to do? All right. What are we going to get? Well, we're still going to get some pyruvic acid. We're still getting that. But now it's going to be very short-lived, because it's going to turn to this lactic acid. And lactic acid, left untreated, will kill the cell. It will destroy the cell membrane. Right? So here's your cell. Here, all right. Here's your cell, rather. Here's your membrane. It's going to destroy that. It's going to eat right through. And when it eats right through, it lets everything out, and, and that's how it dies. All right. But you will get 2 moles. You will get 2 moles of ATP. Right. And let's look at the byproducts. So we get acid, and that acid will be now in the form of lactic. And you get a small amount of ATP. That's all. You don't get the heat, right? So there is no heat. There is no water. And there is no CO2 in this case either. I'm probably lying. There probably is some CO2 there. If I broke this stuff out and did a chemical reaction like H2O plus CO2, plus H for heat, and you probably would find CO2 in here. But don't worry about that. You don't have to worry about that. You don't need to know that. All right, keep going here. So aerobic, like I said, it has detrimental effects, not just to the cell, but, we can look at the sodium-potassium pump, and we'll talk about that probably later, and how that affects that. Because remember, from EMT school, your sodium-potassium pump, right? So you got your potassium, you got your sodium, right? And then you got these channels, right? You got your calcium on the outside, which holds the door open and allows sodium to come in, potassium to come out. Well, what ends up happening is this process starts getting jacked up and it starts failing because the cell is dying, and the sodium potassium pump at the end of the day is responsible for muscle contractions. And your heart, it's a muscle that contracts. And so that's why it's detrimental. Hope that's making some sense to you. We'll get more into that part later. All you need to understand is that it's detrimental. So let's talk about this citric acid cycle and this electron transport chain. I call it a chain. That's what I was taught. I think your book says system, but I'm going to call it a chain. That's what I'm going to call it. So here we are. Glucose comes now. One thing for both of these systems, for this system and for this, you have to have aerobic metabolism, or these guys will not even activate. Okay? Has to be aerobic. All right, next thing. So here we go. Glucose, right? It comes into the cell. It meets who? It meets oxygen inside that cell. The catalyst, it's going to go over to glycolysis. It's from there, what happens? All right, we're going to go to glycolysis. We're going to get some ATP rolling. We're going to get the pyruvic acid. Pyruvic acid now is going to come down here. And this right here, let me change my pen color so that you can see it. Remember what we called the powerhouse of the cell? This is why we call it that. This is the mitochondria. All right? And it's going to be responsible for this process. So pyruvic acid is going to come down here to the mitochondria. Well, something's got to break down this pyruvic acid. And that's where your acetyl CoA comes in. All right, so this stuff right here, it helps to break down. I'm just going to put CoA because you know what I mean. Oh, no, that's not what it does. It breaks down pyruvic acid. That's what it does. All right, let me erase that real quick. Yeah, so this acetyl CoA helps to break down pyruvic acid. All right, and why does that need to happen? Well, why that needs to happen is this. It's all about electrons. Okay, it's all about electrons. And that's what's happening here. It's coming down, and it's got to get the electrons in order, though. It needs to kind of get them organized. And that's what happens. Is they start spinning. They start spinning around, the spinning of electrons. And then from there, these electrons are going to come for their final processing here in the electron transport chain. And that's going to give us the actual 32 moles of ATP. It's that simple. We're not going to make it hard. We're not going to go through all 9 parts of that and the hormones. We're not going to talk about NAD. We're not going to talk about ADP. There's just no sense in it. We don't need to know that. Right? I mean, I spent a whole semester learning that. We don't have a whole semester here. You know, we got other things to learn. So, but I think what they're trying to show you, really, at the end of the day, and they're just trying to tell you how all this stuff works together. That the process is a little complicated, but if you have a lack of energy, you need energy to run this. If you don't have energy, if I'm only getting 2 moles of energy, forget it. This will not happen. I mean, you can tell this is a process. It requires energy, right? And living's not free. Are y'all tired of me saying that yet? I'm going to keep saying it. Just not to drive y'all crazy, but to push home the point. All right, so that's how the energy system works. Let's talk about some other things. Cellular transport mechanisms. All right, so this membrane right up here is amazing. It's amazing because it's selective. Okay? It's selective. It will not let just anything in, and it will not just let anything out. Okay? It will not just let anything in, and it will just not let anything out. but it does stabilize the temperature inside the cell. And that's when we're talking about temperature a minute ago. It helps to do that. It helps to maintain a fluid balance, because I have a slide later and it has percentages of body weight and fluid. And most of your body's fluid is in here, right? It's in this side here. So it helps to maintain a fluid balance from, and we'll talk about it in a minute, between extracellular fluid and intracellular fluid. All right, we'll talk about more about that in a minute. pH balance, yeah, because it helps to make sure that things aren't too acidic or too basic, right? Because you have acids that's being created through all these processes too, and you also have buffers to control the acid, and that all of those are in the fluid. So if it lets too much fluid out, it can become too acidic. If it doesn't let enough fluid out, it can become basic, right? Or alkalotic. Alkalotic. I don't think I spelled that right, but you get my drift, right? You guys understand where I'm going with this. All right, electrolytes. So, I'm sorry, one more thing. It allows for the difference in concentrations, right, between the intracellular and extracellular. Concentrations meaning this. All right, so here's your cell, and here's your cell. All right, so since it's selective, it also makes a concentration gradient. And it makes that gradient because why? Because it will not let just anything in. It lets water in readily. We'll talk more about that in a minute. It lets water in readily, but it will not let large particles in, right? So if particles become large, oh man, I just can't do this right now. My pen. But if the particles are large, well, so water comes in readily, right? No problem there. But particles do not. And so that makes a concentration gradient because the particles get stuck out here. And the water comes in, but the water does take some things in with it. And so inside here, I might have, I'm just going to throw a number out, 80%. And out here, I might have 30%. That makes a gradient. That makes a gradient. It doesn't really, we don't have to make it complicated. It's complicated enough. So, all right, so electrolytes, let's talk about them. So electrolytes, they're chemicals dissolved in the blood. These electrolytes, they make up salts or acids. All right, they make up salts or acids. And so like, oh man. So your salts, this is a salt. Sodium chloride is a salt, all day salt. Okay, bam. All right, so that's a salt. And then it does make up acids too. Okay. But electrolyte is just a positively charged ion. Like this is positively charged helium, a hydrogen positively charged. And so that's all it means. It just has a positive charge, which means honestly it lost something to become positive. And I already explained the concentration gradient. All right. Moving right along. I don't know why I just didn't move. Here we go. Bam. All right. I have a lab I did here in the office so that you guys could see this. I'll post it. But it's diffusion, right? So we'll talk about that in a second. We'll talk about it now. Let me get my pen up. Bam. I think it's working now. Yeah, it is. All right. So look, the natural tendency for anything is understandably is to move from higher to lower. Higher to lower. All right. So, and that's what diffusion does. It's a natural thing, right? So, all right. So here, let me see here. Let's do this. Here's your alveoli. And what's in alveoli? Oxygen. All right. Here's your CO2. Right? Everything, this O2 wants to go down because there is no O2 down here, or very little, right? That's what makes diffusion happen. It's something that is a higher concentration moving to a lower concentration. This is a higher concentration. We're going to say it's 90% oxygen. Down here in the blood, right? So, here's your blood vessels. Here's your cells. Down here, this red blood cell, 10% O2. This is a higher concentration of oxygen, and it wants to go where there's very little oxygen. And the same thing for the CO2, right? 90% CO2, 10% CO2. It's going to want to go that way. Going to migrate from high to low, higher concentration to lower concentration. That's what diffusion is. That is exactly what diffusion is. What do we have here? All right, so look, this is food coloring. And it is a higher concentration. Okay. And there is no food coloring down here, right? No, I don't see any. No, they drop some in. We're going to say low concentration. So what happens? This is going to drop. It's going to go down. And what is it going to do? It's going to diffuse. See this? It's diffusing. And look here. Completely diffused. All the way around. That's diffusion. It's no different in your lungs. It's no different in your alveoli or your hemoglobin. Where we're swapping CO2 from O2. No difference. And here's a picture right here. Here's your alveoli. Here's your warm bed. I like to call it the warm bed. Your small capillaries where gas exchange takes place. Right? These guys are swapping back and forth, and it's going from high to low, high to low. Filtration is another way things get moved around, and what filters better than anything? Yep, you guessed it. I heard somebody say it. No, I'm not that crazy yet, but not yet. But the kidneys. That's their job. They filter, right? And that's how things can get reused, reabsorbed, right? Okay. We'll talk more about the kidneys in a minute. All right. Facilitated diffusion. Did this confuse you guys? You're reading about it? It's really not. It's confusing if you read about it, but hopefully it won't be confusing. Like my speech is, like a stroke I'm having, but no. So look, Facilitated diffusion. This insulin is way too big to get through the membrane. And when the cell was built, it knew it was going to be too big. That's why we have a receptor, right? We have a receptor. And so here comes your insulin, right? And we kind of compare it to a lock and a key. The insulin's going to come in and it's going to unlock this lock. And when it does, the glucose, who's too big to get into the cell, is going to come right through because it makes a pathway for it. Okay? That's what happens. It's that easy. So what happens if you don't have the key to unlock the lock? Glucose can't get in the house. And then you have somebody who would be considered diabetic, right? So when we check their blood sugar and it's 600, can you understand why now? Because the sugar can't get in the cell to metabolize. So where is it? It's floating around everywhere. It's floating around. So when you do a finger stick, it's there. Boom, 600. All right. That's how that works. That's facilitated diffusion. Active transport. Now here's where the fun comes in. All right, because in active transport, we have our cell here, right? We have our plasma membrane. That's selective, right? That makes the concentration gradient. We have poor choices in having any type of receptors. So there's not many receptors, maybe none at all. Or if the receptors are there, it could be the fact that we're moving something that has a low concentration somewhere that we need this, but there's already a high concentration of it there. I should put high maybe. So that goes against the principle, because if I flip back over here, right, you see this, it said the carrier molecules move substances in or out of cells from areas of high concentration to areas of low concentration. Because so far, everything that we've talked about up to this point requires no energy. I'm not even going to put that there. Let's back up. I don't want you to get confused. Right here. Requires no energy. Everything up to this point. Now, when we get over here to this point, it's going to cost us something. It's going to cost us something. So, say for instance, and I guess a really good example of this would be your sodium and your potassium. Right? And we need to get sodium inside the cell, and there's already some sodium a little bit there. So we're going to have to go against the gradient. We need to get the potassium out. But there's not enough of a draw to bring these guys out on their own. And so we're going to have to make something happen, and it's going to cost us some ATP. Right? And so when we do our aerobic metabolism, That's how we pay for it. We have like 36 moles ATP, right? That's how we pay for it. We pay to have this process done, like having your grass cut. You pay somebody to cut your grass. They come and they cut your grass. They don't do it for free, right? They gotta make a living, so you pay them. Well, the same thing here. We're going to pay these guys, but they will not come and do this if we don't pay them. If you're in anaerobic, if you're dealing with ana, you're not going to have to pay. You're not going to have money. You're not going to have the energy to pay the debt. They're going to stop doing their job. And I'll tell you kind of what happens here in a minute in a different slide when that happens. Our endocytosis. All right, so the endocytosis is just a process that it costs energy, right, of substances coming into or out of the cell. There's three forms. There's penocytosis, phagocytosis, and then receptor-mediated endocytosis. All right, we'll talk about them. All right, so penocytosis is kind of like when the cell drinks. That's what they call it. That's what they say. Because what ends up happening is this, whatever the substance is that comes down, but as it is a liquid, it will be a liquid. It's going to come down. It's going to land right here, right? The cell wall is going to curve in just like that, and it's going to vacuum it in. It's going to vacuum it in, but guess what it's going to do? It's going to keep it protected. It's going to put it in its own little cell so that, that this thing doesn't get crazy. Try to do something inside the cell that it's not supposed to do. Remember those vesicles that I talked about? Those vesicles, it's like a tube, right? That vesicle is going to go in, it's going to pierce that cell, and it's going to drink whatever liquid's in there. Now, you're going to see a lot of this kind of stuff in your infection-fighting cells. If this liquid was a foreign type of liquid that didn't belong in the body, that's how the body's going to deal with it. Let's talk about now what happens if it's something else. So here's the difference, like phagocytosis, right? This is for liquids, and this is for solids, all right? Or bacteria, maybe, too. So bacteria is floating around, all right? And so this bacteria lands right here into this part. The cell makes that indentation and just sucks it right in. But what's it do? Keeps it in a cell. Then another cell is going to come along, or it could be this cell. It's going to consume that like it's eating it. Yep, it's going to eat it, plain and simple. It's going to eat that, and it's how it's going to get destroyed. It's going to destroy this bacteria. But it's like Pac-Man. I don't know if you guys know that game or not. All right, but anyway, what happens when you eat as a human? You go and say that you go, grab a quarter pounder, some fries, drink a big Coke, right? And let's say you hadn't had a quarter pounder in 4 months, been dieting. This was your cheat day. What happens about 20 minutes from then? You better be near a bathroom, right? Because it is coming out. Well, that's going to happen here. What? Yep, it sure is. And I'll show that to you in here. And that's called exocytosis. After it does its job here, the vesicle gets involved and it will send it back out the cell. But it keeps it protected, but then it comes back out. And once it gets it, it just poops it out into the extracellular fluid. All right, receptor mediator endocytosis. All right, so this is like kind of like what it says. All right, so it's it can be it's a little complicated, but not too bad. All right, so let me try to explain this. So here you have a cell. I'm sorry. Let's call this a bacteria. Well, it's gonna float and it's gonna run into a receptor, and these receptors will mark this as a bad cell, or not even a cell, you could say, I guess you call this a cell and you could call it a bad cell. This is a bad bacteria and it's going to harm us. And so the job of the body sometimes is to tag this chemically and puts a chemical tag on it. And then what happens is the body goes, oh, okay, I got you. It draws it in. These guys, see, they go in and out of the cell. Here's one. So they're just outside and inside the cell membrane. So they're able to make this happen. And so what they do is just like earlier I showed you. It gets it in, sucks it in, and puts it inside a these are coated vesicles. And it does the same thing as I said before. It eats it and then poops it out. That's it. All right, osmosis versus diffusion. We just talked about diffusion, so let's talk a little bit about osmosis. So when we're talking about osmosis, there's a couple things there's a couple things that they share, and then there's things that makes them very different from each other. And what makes them very different from each other, this is a movement of solvent particles, all right, across a semi-permeable membrane. This is a huge difference between osmosis and diffusion. Is that a membrane? All right, hang on one second, guys. Let me pause you for a second. Okay, guys, we're back. Yep, just had to deal with that real quick. All right, so the differences, right? Or we're talking about osmosis. All right, so these solvent particles have to be water, and the semi-permeable membrane has to be involved as well. With diffusion, you don't have to have that. We'll talk about it next slide, I think. But osmosis from a dilute solution to a concentrated solution. The solvent moves to dilute the concentration solution and equalize the concentrations on both sides of the membrane. But here's the problem. Here's your cell. Remember I said water goes in readily, right? When we're talking about diffusion, there's no problem going in or out. So the cell wall in diffusion is not a problem. Problem is when we start talking about concentrations, and usually osmosis, we're talking about concentrations. So let's say, for instance, let's just use sodium again. I'm going to throw a number, 70% concentrated. All right. We're going to have sodium here. We're going to call it 40%. And we're going to have water. Okay. All right. So what do you think is going to happen? The water is going to come in with no problem. but the sodium is going to be blocked, right? And it'll be blocked because of the membrane. The membrane is not going to let that sodium in. It won't do it. It's like you're blocked. We're good. So it will never be, it can be equal depending on what's going on, but that's the goal. The water, it doesn't understand that. It's like, I got to come in here. I got to make these guys equal, whatever, blah, blah. So it's trying to equalize, but the sodium gets left behind. And that's why sometimes it's not equal. With diffusion, it's always equal. Always equal. All right. Let's continue. All right. So here's some similarities. Both equalize the concentration of two solutions. That's kind of a false statement. Both try, or both, that's what both do. One's successful all the time. And, I'm not going to say osmosis is not successful at certain times, because it is, but it's, like I said, osmosis, guys, I want you to think about the cell membrane being involved. And with diffusion, don't think about, even if the cell membrane's involved, diffusion is not hampered by it. All right, so they're both passive transport processes. What does passive mean? All right, no energy. No energy debt. Okay, so that's a good thing. They both have a good quality there. Both of these guys are moving from a higher concentration to one of lower concentration. All right, so, and let me try this. So here's your sodium. Make it 30%. Right, and your sodium out here could be, maybe 70%, right? But that 30% might be what the cell wants. I don't know. But if the cell membrane doesn't want it in, it's not coming in. That's why, even though it's attempting to do its thing in osmosis, it won't happen. But anyway, this is the common stuff right here. This is what qualities they share. But here's the differences. So when we're talking about osmosis, we're talking about only water, okay? Or another solvent, meaning another liquid. So we're talking about liquid, right? And then when you talk about diffusion, any type of substance. So we could be talking about what? A gas, like O2, CO2, right? We could be talking about a liquid, or we could be even talking about solid. All right. Osmosis, again, only a liquid. All right, diffusion can occur, and I already said that. Osmosis requires that a semi-permeable membrane be involved. Diffusion could care less. It's like, I don't care. That's not going to stop me. I'm going to do it. Kind of like my kids. There's a parent involved. Oh, there is? Oh, I don't care. Kind of like that. And then I got it right here. The concentration of the solvent does not become equal. And the solvent is what? It's not the liquid. Right? The solvent would be like the sodium, the calcium, something like that. That's your solvent that may be submerged in the liquid, right? So yeah, that's how that works. In diffusion, yep, it's going to equalize. It's going to be equal. All right. That's your differences. Hang in there, guys. We're almost done. All right. Let's talk about this. Is important because you guys are going to be pushing fluid out there, right? You guys will be starting IVs. You're going to be administering fluids. And so when we do, you got to worry about the cell. And so let's talk about some terminology. Tonicity, right? That's a relative concentration of solutes, right, in two fluids. I don't know if I wrote that down right. Relative concentration of solutes, all right, in two fluids. Okay, we'll talk about it in a minute. All right, but for something to be tonic, and we're talking about the strength or tone. All right, so we'll get to that in a second. I'll come up with a way to use that. All right, so because water can diffuse across the cell membrane easily, right? We talked about that. The ability of the cells to control its volume depends on the tonicity of the extracellular fluid, right? The concentration, right? So here's your cell. Here's your extracellular fluid. Okay. And your intracellular fluid. All right. So how strong it is, right? How strong is your extracellular fluid? Because that's what it says. It says to control its volume. What's it mean by that? I'll tell you. Depends on the tonicity, right? All right, so we got some sodium in here, right? We have some sodium out here. If this cell lets too much concentration of sodium in here, what's going to happen? Well, water's going to rush in there. Because wherever sodium is, water wants to be too. So if it doesn't control that concentration of sodium out here on this side, it's tonicity. So let's say it has a lot of sodium. A lot of sodium, right? It's strong sodium. It's coming in, right? So it has to control that, because if it doesn't control that, this is going to start swelling. And it's going to burst, or another medical word is it's going to be it's lysed. All right. I don't know if I spelled that. Do I have that word up here somewhere? I think it's Lyse, or anyway, you know what I'm saying, right? So what happens is, look, here's a normal cell. What happened here? Oh, the cell membrane's gone, and it's going to bust wide open. And that's hypotonic. So if it doesn't control all this, that's going to happen. So let's erase this now so we can explain the other ones. Sure. All right. Here we go. All right, so let's talk about isotonic. What were those slippers' name? Were they iso something? Isotone slippers? And I think that's what they called them. And isotone is going to feel good to the cell. It's going to bathe the cell. And the reason why that is because it's the same cellular, it's the same makeup of the cellular fluid. So in this case, 0.09 normal saline. That's what we carry here, right? Is isotonic. It's equal to the solute of concentration of the intracellular fluid, right? So great. But what if we screwed up? And I almost did this one day. at the hospital. I grabbed the wrong bag of fluids, and I can't remember what the concentration was. Let's say it's just 0.24 normal saline. All right, what's going to happen? Well, in this case, it's going to cause this concentration of solutes higher than the intracellular fluid water, right? So here, you're going to have 24% saline out here, or whatever, you know what I'm saying, right? 0.24, and it's gonna draw water. It'll draw water out. Remember, water wants to go where sodium is. It's going to follow sodium. So what's going to happen to that cell? It's going to shrink. It's going to shrivel. Hold on one second, guys. Okay, we're back. Sorry about that. So yeah, the hypertonic is definitely going to make the cell shrivel. Okay, let's continue. Almost done, guys. The body fluid balances slide is here, just so you kind of get an idea of how what the differences are between the intracellular fluid and extracellular fluid. Special note here. It just kind of gives you an idea, lets you know that, quite a bit more intracellular fluid than extracellular fluid. Intracellular fluid is going to divide further, though. It's going to divide into your blood plasma and into your interstitial spaces. Okay, and it's like between the cells. The whole idea, though, goes way back like 8 slides ago when I was talking about fluid balance. Yeah, the body has to control the fluid balance along with concentration to maintain homeostasis. All right, and the last slide here talks about ADH. Okay, so a little bit of a central nervous system thing going on here. You have ADH, it's your antidiuretic hormone. Okay, and in the brain. Okay. Right. And so what ends up happening is the osmoreceptors, they pick up on an increase in sodium. And so that means that we're losing too much fluid. It's going to secrete a hormone from the pituitary gland. The hormone's called ADH. ADH is going to go to receptors on the kidneys. Okay, and it's going to do a couple things. One, it's going to say, "Hey, cut back. Let's hold on the urine." And it's going to say, "Let's reabsorb as much water as possible to take that back to the plasma," right? Because we're lacking at this point. I don't know if you guys remember in EMT school when we talked about shock, and we talked about vasoconstriction, and we talked about epi and norepi, and those are responsible for vasoconstriction. But what was the side effect of that besides elevated heart rate? Well, the side effect of that is it affects the sweat glands. All right, and so your sweat glands are activated. So that's why you can have somebody who's doing absolutely nothing, 50-year-old male, cardiogenic shock, sitting there sweating like a fiend. Okay, well, the whole reason behind that is that's because the sweat glands have been activated. Well, same thing here, ADH. you're going to activate the thirst part of that, and the patient's going to be extremely thirsty. All right, guys, that's it. That's all I have. I'll post this very soon. It's going to take a minute to upload. It should have been done yesterday, but it crashed on me because it's such a long video. And so hopefully this one won't crash. If it doesn't, have it out to you today. Have a great rest of your week. Study hard, and I will be talking to you shortly.